This problem is the AP Calculus AB 2019 question number 6 on the free response. As such, this one would be non-calculator. In a normal year, the last four would be non-calculator for the exam. Let's read through the prompt, identify some information, and see if we can answer these questions. I'll also be trying to help you with how to earn points and how those points can be earned for each individual section. Here we have functions f, g, and h, and those are all twice differentiable functions. That's right here. That's good to know because that indicates continuity and also differentiability. If a function is differentiable, it's definitely continuous. We also know that g of 2 is equal to h of 2, which is equal to 4. So g and h, when x is 2, both have an output of 4. We also have the line y is equal to 4 plus 2/3 times x minus 2, and that's tangent to both the graph of g and h at x is equal to 2. And we can see that here because our x value is 2, and then our y value is 4. Another way of writing this would be y minus 4 is equal to 2/3 times x minus 2. And we can also see our slope right here, slope of the tangent line being 2/3. So if you pick that one apart, you can actually figure out some good information. And it confirms what we know about g and h from right over here, that when x is 2, y is 4 for each one of those. For part A, we want to find h prime at 2. Well, h prime at 2 is the derivative or the slope of the tangent line to h when x is 2. So if we take a look at our tangent line slope right here, that's going to be 2/3. You actually are going to get 1 point for that on the exam for just writing down 2/3 for this one. Now, if you totally draw blank, I would recommend writing something down. And then actually, if you have to use that value in a future problem and you use the incorrect value correctly in a future problem, you have the chance of earning points for that future problem. If you don't write anything down and you have to use that value later, then you might lose points because you don't have anything down. So on the exam, all is not lost. If you are drawing a blank on something, make up a number you think is believable, but just write something down. For part B, we have let a be the function given by a of x is equal to 3x to the third times h of x. So that's going to be actually important for us here. We're going to write an expression for a prime of x and then also find a prime at 2. So if we look at our a of x, we want to find the derivative here. We have to use the product rule. So a prime of x will be equal to 3x to the third power times h prime of x plus h of x times 9x squared. You're actually going to get 2 points on the exam for writing that. You'll get a point if you have something that looks like the product rule. You'll get a point if you find the actual a prime of x or the expression for a prime of x. I wouldn't do anything to this one right here. Although if you really wanted to, sometimes on the answer keys, you'll see the 3x or a 3x squared factored out. So I wouldn't really do this, but if this is something that you wanted to do or makes better sense to you, you could factor out a 3x squared and you'd have x times h of x, or h prime of x, excuse me, plus 3 times h of x on the inside of a big set of parentheses. And that could be a multiple choice question if you got to take that multiple choice portion. Okay, let's move on though with the original a prime of x that we found here. And what we want to do now is we want to answer the last part of this question, which is to find a prime at 2. So that's going to be 3 times 2 to the third times h prime at 2 plus h of 2 times 9 times 2 squared. What I would do next is I wouldn't do any simplification for this other than getting the function notation out of there. You do have to do that. So let's focus here on h prime at 2. Now h prime at 2 comes from the previous one, and that's going to be 2/3. So that was one that we just found before. Once again, if you didn't find it to be 2/3, let's say you found it to be 4 or something, if you use that correctly in this part, you should earn points for that in this part. Obviously, you wouldn't earn the point in part A because you didn't get the value correct. Then h of 2 we know is 4. On the exam, leave this line right here. This is a valid numerical expression for a prime at 2. If you did simplify it, you would get 160. So for more fun, go ahead and do that right now if you want, but don't do that on the exam. Just leave the numerical answer as it is. You can see I didn't even simplify the 3 times 2 to the third or the 9 times 2 squared. I just wrote the same thing down. Less chance for mistakes that way, and less chance, or excuse me, it's more efficient rather. You won't waste time trying to simplify everything. So this one's 3 points here. Once again, 1 point for using some form of the product rule, another point for getting a prime of x, and that's this step right here, and then another point for getting the numerical or a numerical expression that's equal to 160 for your a prime at 2. Let's move on with part C here, and we now have a function h that satisfies h of x is equal to x squared minus 4 over 1 minus 4, or excuse me, f of x to the third power. So that's going to be probably pretty important for us here. And we're told that that happens when x is not equal to 2. It is known that the limit as x approaches 2 of h of x can be evaluated using L'Hopital's rule. So that might be a help to us. We'll see. We're going to use that limit to find f at 2 and f prime at 2. So here we'll do f at 2 in blue, and then just to differentiate a little bit, we'll do f at prime or f prime at 2 in red. So let's work with the first one here. So for this first one, we need to set up a limit. Now, if we have the original function here listed in blue right here, we're going to take the limit of each side. So we're going to do the limit as x approaches 2 of h of x, and that's going to be equal to the limit as x approaches 2 of x squared minus 4 over 1 minus f of x to the third power. You'll actually earn 1 point on the exam for setting this equal to 4. Remember that the value of h of 2 is 4. So this left-hand side is equal to 4. And then what you'll do is you'll actually substitute the 2 in here. So you'll get 2 squared minus 4. And then we'll have 1 minus f at 2, and that whole thing has to be raised to the third power. So you'll earn a point for setting the limit as x approaches 2 of h of x equal to 4, and then making that equal to the limit as x approaches 2 of the entire function itself. Let's try to solve this for f at 2, which is where your second point is actually going to come from here. So in this case, I'm going to multiply by the denominator. So I'll have 4, and then I'll have 1 minus f at 2, all raised to the third power here, is equal to 2 squared minus 4. Well, 2 squared minus 4 is 0. So here we just multiplied by this entire piece on each side. 1 minus f at 2 to the third, and 1 minus f at 2 to the third. That's what you see here, and then those guys will cancel. We're just removing the denominator. And we can also now divide by 4, and we find 1 minus f at 2 to the third power has to be equal to 0. And if we add, or excuse me, subtract 1 and divide by -1, or add f of 2 to the third power to each side, we wind up with f at 2 to the third power being equal to 1. Taking the third root, or raising each side to the 1/3 power, we find f at 2 to be equal to 1. So there's where your second point is going to be earned. So the first point is kind of for the setup, and then the next point is for figuring out the actual value. Let's go ahead and work with the next one, and here we want f prime at 2. So here we have the limit as x approaches 2 of h of x. We're going to write the same thing down we did before. The limit as x approaches 2 of x squared minus 4 all over 1 minus f of x to the third power. Same thing, same start. Here we also know that that limit as x approaches 2 of h of x is equal to 4. And we also have 2 squared on the right hand. Excuse me, we want to take the limit in the numerator as and then actually for this one, we're going to take the derivative of the numerator and the derivative of the denominator. So if we take the derivative of the numerator, we're going to wind up with, oops, got to keep the limit notation down, the limit as x approaches 2 of 2x all over the derivative of the denominator, which is 3 times f of x squared times f prime of x. There's your chain rule. Notice the derivative of 1 is 0 and the derivative of -4 is 0. That's why you don't see them anymore. And then what we'll do here is we'll actually substitute that 2 in. So we'll have 2 times 2 over 3 times f at 2 squared times f prime at 2. The next step to solve, we're going to multiply by the denominator on each side. So we'll have 4 times 3 times f at 2 squared, which, by the way, f at 2 happens to be 1. So we could actually sub that in, and that's going to be 1 squared, or 1, times f prime at 2. And then we've got that equal to 4 here. And I forgot a negative sign up above. Apologies there. Should be a negative sign right here and right there. And then we've got that is going to be equal to 2 times 2. That's this piece right here, which is 4. And we can see here that the coefficient of f prime at 2 will be -12. So we'll divide each side by -12, and we find f prime at 2 to be -1/3. So this is a 4-point problem. We got the 2 points for the work in blue, and the breakdown for the work in red would be using L'Hopital's rule. So that would be from this step right here to this step right here, where you take the derivative of the numerator over the derivative of the denominator. The next point would be earned for finding that numerical value for f prime at 2, which happens to be -1/3. We have one part left to do, which is part D. So in part D, it's known that g of x is less than or equal to h of x. So g has lower y values than h over the interval 1 to 3. And k is going to be a function satisfying this piece right here. So we know that g is less than or equal to k, which is less than or equal to h over that interval. K, and the question here is k continuous at x is equal to 2? So that's our question, and we want to justify a response here. Now, if we think about it, k right over here is being squeezed in between g and h. To prove continuity, we need a couple different things. We need the limit as x approaches 2 of that function to exist, and we also need that to be the same as what the function is defined at when x is equal to 2. So a couple different pieces here. We can say here that g and h are differentiable and therefore continuous. So we can say g and h are continuous. We know that because in the previous prompt of the problem, the original problem there, is that g and h are twice differentiable. So they're definitely continuous. And let's see, g of x is less than or equal to h of x over that interval. Therefore, the squeeze theorem applies, or is applicable, you could say. So what does the squeeze theorem say? The squeeze theorem says that over an interval, if one function is always lower than another, and also that we can tell that here with and then the middle function is between the other two here. That's this piece right over here. So g of x is less than or equal to k of x is less than or equal to h of x. And we also need g to be the same as h at 2, which is actually true. Then we can use the squeeze theorem here. And the squeeze theorem is going to state that the limit as x approaches 2 of g of x has to be less than or equal to the limit as x approaches 2 of k of x. We're just taking the limit of everything here. And that's going to be less than the limit as x approaches 2 of h of x. And of course, we know what those limits are except the middle one. And we know the limit as x approaches 2 of g of x is the same as g at 2, which is 4. And then we got that squeezed in between here, the limit as x approaches 2 of k of x. And then, of course, the limit as x approaches 2 of h of x is also 4. H at 2 is equal to 4. So we can say here that, therefore, the limit as x approaches 2 of k of x also exists, and it is 4. Squeeze right between those two numbers. Those two numbers have to be the same on the left and the right, and if so, then you've got that limit down pat. We also know that according to our this guy right here, our inequality, we can take g of 2 and substitute that, or substitute the 2 into each one of those functions, and then it'll be h of 2 over here. So we also know that g of 2 is 4, and h of 2 is 4, which means k of 2 has to be equal to 4 as well. Now let's answer the question. So I like to go back and see what the question is asking us. It says, is k continuous at x is equal to 2? And we can say k is continuous. Oops. When x is equal to 2, and the justification is pretty much what we wrote above, but you can add a little extra line that says, because the limit as x approaches 2 of k of x is equal to k at 2, which is 4. And this line is our continuity test, our three-part kind of test here. The limit as x approaches 2 from the left and the right has to be the same, and it is. And that limit as x approaches 2 exists, and that's the same as k at 2. And you'll earn 1 point for this on the exam. You have to state that k is continuous and also the reason why.